Aniruddhe, the floor is yours.
Thank you for the introduction. Welcome to this presentation. I am Aniruddhe, and the title of today's talk is Mathematical Formalisms and Data-Driven Approaches for Coarse-graining of Multiscale Finite Element Discretizations. This work was done under the supervision of my advisor, Professor Zwanzig, and I would also like to thank the committee members for all their help during this project. With this, we'll start the presentation. So this is the brief outline of today's talk. So first, I'll start with the background on multiscale processes, move on to the MZVMS framework, develop certain insights from the MZVMS framework, and transfer this knowledge to another data-driven framework, which we call the Variational Multiscale Super Resolution approach, and then use insights from part A and part B to do some wall modeling with the goal to improve existing slip wall models. And finally, I'll present some contribution of my work and some perspectives that we developed during this course of this project. So we'll move forward with the background of multiscale processes. So multiscale processes are quite ubiquitous in nature. You find them everywhere. And these processes have this feature that you can model these processes at different levels of approximation. And at each level of approximation, what you essentially get is a system of ODE and a PD. And for example, if you take the case of fluids, you can actually do molecular dynamics, you can solve Navier-Stokes, but what method you want to use depends on what is your quantity of interest, what you want to see, what are the physics that you want to see. At each level of approximation, you get an ODE and PD, but these PDs can itself show hierarchy, given there is certain parameters which trigger multiscale behavior. Above are some of the solutions of some of the PDs showing multiscale behavior, and we are going to talk about multiscale PDs mostly in this work. So one of the multiscale PD is Navier-Stokes. It shows complex multiscale behavior. You will have scales which are as small as the Kolmogorov length scale, and there will be scales as big as your geometry, size of the geometry. And what triggers this nature is the parameter that triggers this behavior is the Reynolds number, and you essentially also find similar hierarchy in the temporal length scale as well. If you want to simulate these kind of flows, the cost goes up to the power of RE cubed, but in general, we are mostly interested in some quantities like mean velocity or some low order statistics, and hence we need to develop coarse-grained models. Another motivation would be that numerical simulation is very important now for most of the science and engineering applications. And by 2030, NASA plans to actually do calculations of maneuvering in flight or model LES simulations. And to make these simulations practical, we need cost-effective methods through coarse-graining of multiscale partial differential equations. Now that we have established why coarse-graining of multiscale partial differential equations are important, these are the general principles that is followed if you want to coarse-grain a PD. You start with the PD and then apply a coarse-graining operator. And what this operator is depends on what you want. Like it can be average, it can be a filter. And essentially, the application of this term on the PD gives you an unclosed term, and which you need to model. And this is called the closure modeling problem, and the model is called the closure. In this work, we are going to use three things together: data, formalisms, and physical insight to actually do the closure modeling. Now that we have discussed what closure models are, these are some of the properties that I desire. That it's there's no consensus in the community which one of these properties are important. But some of the properties that you would like is it should be formalism driven, which means you should have minimal phenomenological bias. Because if you look at the timeline of these models, it took up quite a long time to develop these models. Hence, you need formal process through which you can actually derive these models through natural, through tools, like formal tools. Another important properties you would like to have is that it should have perfect scale decomposition. You should know precisely what you are resolving and what you are not. Accuracy is still something hard to define for LES because it's really possible that you can get the exact subgrid stresses you can model the exact subgrid stresses. Rather, it's the ability of LES model to create correct flow statistics. It should be adaptive, which means that you should be able to get parameters in the model automatically, and it should also be stable, which means addition of that model should not blow up your simulations. It should be efficient to compute. That's what the goal is for any closure model. And finally, one of the properties that we want in data-driven models is model consistency, which means that the model, when goes inside the code, should essentially be giving you desirable outputs from the solver. So this is the brief overview of today's talk. So this work is distributed into 3 parts. First, we will be using formalism-driven approaches, where we'll be mixing concepts from statistical mechanics and variational multiscale method to develop closure models for the continuous Galerkin finite element discretizations. Then we will move on, use some of the ideas from VMS to develop a data-driven subgrid modeling framework, and then finally use ideas from part A and part B to develop a unifying perspective for LES, RANS, and wall model LES with the goal of improving the existing wall models. So we will move on to the first part of this presentation, which is the MZ-VMS framework. So as the name suggests, it's made up of 2 methods, MZ and VMS. So we'll first describe the VMS method. So the idea is that, so this is the original work by Hughes. Like this is the first, so this is the vanilla version of VMS, where he actually took a linear PD and wrote down the variational form for this PD, and then decomposed the solution and the weighting space in terms of fine and coarse scale components, leading to 2 equations. If you have done LES, it's pretty much similar, except that you get 2 equations. However, your goal is to just solve the first equation, which is the coarse scale equation. The goal of VMS is to approximate the second equation to get an explicit equation for U dash, so that you don't need to get solutions from the higher order term, essentially closing the first equation. And this is precisely what is done in VMS. So in VMS, since it's a linear problem, you can always use the Green's function approach to get an analytical solution for U dash. However, it's really the case when you actually need the actual solution. Rather, you always need to make an approximation of U dash. So when you substitute in the approximation of U dash into the coarse scale equation, you get an equation which is explicit for coarse scales. And it has 2 terms. The first term is essentially the Galerkin approximation, if you don't assume a VMS-like approach. The second is the closure term that comes from the VMS approach. So in summary, you want to coarse-grain a PD, and you end up with an equation that only governs the coarse scales. The second part of MZ-VMS is MZ. So this is a model order reduction strategy for OD systems. For example, if you consider the case of just 2 degrees of freedom, and suppose it's a linear problem, so it's an easier problem, and you just want to write down the evolution of X without taking into consideration the evolution of Y. So you can actually use the integration factor approach to do this. And this is precisely the goal of MZ. However, this is true, the integration factor approach works for linear problems, and to make sure that if your system is nonlinear, you have to convert it to an equivalent Liouville form, which is a PD in the system of initial conditions and time. And if you put the initial condition of this PD as any observable, what you would do essentially is that the solution of the PD would be actually the solution at any time t of that observable. So if you select the observables to be the same as the variables that you want to solve, and if you write it in a shortcut form, which is the semi-group notation, and you can write the first equation. You can then expand the right hand side in terms of projection operators. These are different projection operators. These work in the phase space, but application of the projection operator truncates the variables you don't want to resolve. Essentially, final step is to apply the Duhamel's principle, which is kind of like the integration factor approach for linear PDEs. And finally, what you essentially get is an equation that only governs the system of resolved variables, the variables you want to resolve. So in summary, you start with the ODE with lot of variables, and you end up with the ODE system in which you only have the variables you want to resolve. Now that we have seen what MZ and BMS is, we want to combine this together in one single framework. So the goal is to again start with the nonlinear PDE and write down its weak form, and then try to write down the evolution equations for the basis coefficients of the resolved and the unresolved variables. So now what we'll do is we'll use the MZ to actually eliminate the second part and try to get an equation that only depends on the coarse-scale variables. The good thing about this is that it is completely developed in a nonlinear setting because we don't have to use the Green's function approach. One of the other approximations that we are going to do for the CG approach is that we are going to assume that the subscales actually vanish at the element boundaries. So in summary, you start with the transient PD, end up with an MZ closure. The closure for any PD would look something like this for the CG approach. Exemplary for the Viscous-Burgers equation is shown in the equation below. And if you look at the form, it is pretty similar to the adjoint stabilization approach, except the residual is computed in place of the residual, the projection of the residual in the fine scale is used. Now we will, so although we actually derived this closure, one parameter that is still we are yet to calculate is the tau. You can see a tau parameter which is completely up to the user to give. So you want to compute tau, and if people who are familiar with LES know that there is a principle by which you can actually compute tau dynamically using the German-Reynolds identity. And this is precisely what we do. So we write down the MZ closure at two levels and try to eliminate the full order term, essentially getting an equation connecting tau1 and tau2, where tau1 and tau2 are the values of memory length at two different levels. However, we don't know what's the relation between tau1 and tau2. So what we are going to do is we are going to use a scaling law that was proposed by Dr. Parrish and Professor Dureshwam in 2017. However, still there is a problem of this system being overdetermined because this is true for any coarse-scale basis functions. So we have to use some approach like least square or take an average value to ensure that we can get just one tau for the entire system. And this is precisely what we do. So the first problem that we solve is the Viscous-Burgers equation. In this problem, the viscosity is pretty low. So if you start with a sine wave, it is going to steepen and eventually form a shock. If you are not well resolved, your solution will go unstable. So you have to add some stability. So this, so we actually plot the tau for three different methods, and we find that all the three methods work pretty well. But we are going to use method 3 because although for these problems they are equivalent, the third one was found to be more stable for the other approaches.
What is L and R?
It's basically so if you substitute tau1, this is the right and left. So basically, it's like the mm term by rm term.
Left and right hand sides of those equations. Got it.
So we'll move on to a more complicated problem, which is essentially the 3D decaying homogeneous isotropic turbulence, and the Reynolds number based on Taylor length scale is 64. As you can see, for 64 cube linear elements, all the methods work pretty well. the OSS model, which is our model of comparison, which is the orthogonal subscale model, is slightly more dissipative at the higher wavelength, where the energy is slightly less. When we increased the Reynolds number, we found a similar behavior. Again, the OSS is slightly dissipative at the higher wave numbers, where you can see there's a shortage of energy there. However, when we increased the RE lambda to 164, we found that all the models fail. And one of the reasons that was given in one of the papers was that these models are very good in predicting the cross stress. The Reynolds stress is hard to recover, especially at very high Reynolds numbers, where it dominates. So this brings us to the end of part A. So what we did was we developed MZVMS CG framework that allows us to come coarse-grained continuous Galerkin in the continuous Galerkin framework. And we didn't use any phenomenological assumption while we were actually deriving these subgrid closures. We also used dynamic modeling to accurately predict what the tau value would be. We showed that this method works for a variety of problems. Results for the Taylor-Green vortex case and Burgers turbulence are there in my thesis. And what you find that the finite modeling approach that we use doesn't work at extremely coarse resolutions. So I'd like to take any questions that you have in this part before I can move on to the next part.
A quick question, either online or.
So in the first part, we actually observed that you can actually write a precise form of subscale using the Green's function approach, but it is rarely the case that you actually need the precise form of subscale, rather you always need an approximation. So an approximation can be found by just projecting the fine scale into a space which is finer compared to the coarse space, but coarser compared to the exact higher dimensional space in which the U dash exists. For the convection diffusion equation, you can precisely write down it in this format, which is essentially that the normalized form of subscales when it can be written as sum of products of normalized basis coefficients times function of the physics informed parameters such as the self-Peclet number. And also it just depends on the projection of the Green's function. So as long as you can learn the projection of the Green's function, you are good, and you should be able to precisely learn the subscales. So, which now means that we can actually use data to learn this. And one of the examples is shown on the figure on the top, where we are actually taking the solution from a high dimensional finite, like we are solving the convection diffusion equation using finite difference method on a very high resolution mesh, and then computing the fine scales. One another issue is that the alpha can vary if you are actually making a model, so you should always use features such as log alpha, essentially ensuring that your alpha values that it doesn't blow up when you enter your alpha value in the model. Similarly, when we actually extended this approach to high orders, we could actually learn the closures. So this plot that is shown below shows the solution for two elements, global Peclet number of 40, where you can actually learn the subgrid model for P7 and P8, showing that this method is pretty accurate in doing that. So now that we have established certain points which help these kind of approaches, so we can use data-driven approaches in these approaches. We can use data-driven techniques for these approaches. We'll now show more results using this, but before that, we want to connect it to some of the existing solutions that are some of the existing problems that have been already done, and how does it connect with that. So in this work, what we are essentially going to do is we are going to super resolve the finite element solution from low order to high order. So if you look at this problem, it is not much different from what we have been doing, because essentially the difference between the fine solution and the coarse solution is essentially your subscale. And this is also very similar to what approximate deconvolution method does. And most of the work that has been done in the literature are for reconstruction only. So we are actually using a model, a super resolution model, to actually improve the performance of the numerical method. Other kind of applications that we think where this approach can be used is error estimation, and others are already presented in this work. So essential to any training of super resolution model is generation of data. So the way we are actually generating data for this case is we are taking the DNS solution and then L2 projecting it on basis functions. And so what we are doing is we are taking the high resolution solution, projecting it on different grades. For each grade, we are projecting it on 2 polynomial orders. It can be, the low order is always P1, the fine space can be 2 or 3 based on the application. And then we are trying to super resolve it from P1 and P3. And for each case, we are actually calculating normalizing parameters and physics informed parameters. The reason we are doing this is because we want to ensure that our model doesn't just work on one grid, but it generalizes to different grids.
Aniruddhe, can you clarify? I'm not familiar with this idea of super resolution. Can you
So the idea of super resolution is just that you have a coarse solution and you apply an operator and you should get the fine. So this can be just thought of as filtered quantities.
It's like upscaling.
So essentially the P3 will have more information, and so P1 to P3. So as we have already seen that the subscales have a particular structure that we already discussed in a form of sum of products, we are now going to impose this structure in our network. So essentially the network that we propose is the VSRNN, which has 2 parts. The first part is essentially takes into consideration the normalized basis coefficients of the coarse scales. The second network essentially takes into consideration function of the physics informed parameters, and in between we are doing products of these outputs, and there is a final network which actually combines them and outputs the subscale basis coefficients. And these physics informed parameters can be anything like cell Reynolds number, can be Peclet number or CFL number based on your problem. But before we move on to a more complicated problem, we wanted to try it on a simple problem, which is the linear advection equation. So these plots are the space-time plots of the solution. And we are again projecting this solution on different grids. And for each grid, we have a P1 solution and a P2 solution. And we are trying to super resolve the P1 solution to the P solution. And we are training on one initial condition and predicting it on another initial condition. And what is pretty observable is that as the CFL number increases, the reconstruction performance kind of decreases. So if you look at the columns, this is essentially the second column is essentially the prediction, and the last one is the actual what you should expect, and the last one is the error. But this doesn't, we should not end it to the reconstructive step only. We should also ensure that this can be used somehow, and we actually bring back the VMS method. So to do the linear advection, you can start with again the weak form, do integration by parts, and use space-time elements here because we are doing a space-time formulation. If you take the space of your core space and space of the solution to be the same, then it's the traditional method. But what we are going to do is we are also going to take care of the subscales, but the subscales now come from the neural network model that we just trained. So when we actually used that subscales into the VMS formulation, what we observed was that our method was much better, which is marked by SR. The projected DNS is essentially the model of the solution of comparison. And also the subscales are also pretty much accurately resolved. And in fact, the traditional model is pretty dissipative, where you can actually see that it becomes whiter with time, essentially saying that the peak actually decreases. And this is also shown in the traditional method plot. Moving on to a more complicated problem, which is the turbulent channel flow problem. Here what we do is we take snapshots of channel at different wall normal heights, again do the projection on P1 and P3, and try to learn the solution from P1 to P3, and try to predict it on a different solution. So the top one is essentially the coarse solution, and we are predicting the second row. And you can see that there are more discontinuities in the first one, which is relatively less, but it's very hard to actually see. It's actually, you can see that these plots are not very much the same, and this problem actually is more complicated for a turbulent flow case. But what we observe is that although they are not like pointwise similar, but the spectra-wise they are similar, saying that statistically whatever the neural network created was kind of okay in a statistical sense, but not pointwise. So when we actually use this network again in the prediction step, we actually found that addition of the subscales to your solution led to an unstable formulation. So we had to under-relax this solution. We found that we could under-relax up to 0.2. Essentially, lambda is equal to 0 would mean it's an implicit LES with rho flux, and lambda equal to 1 means you are actually evaluating with the subscales. And you can see till 0.2, the results actually improved for the streamwise components. For the other statistics, it was quite the same. So in summary, we can say that we actually derived a unified data-driven super-resolution framework. We made the network architecture consistent with existing formulations from VMS. Not only did we do offline reconstruction, but we also used the solution to improve the solution, the accuracy of the numerical method. For linear problems, for the linear adduction problem, it was just led to a highly accurate numerical method. For the channel flow case, it led to slight improvement, but stability is something we need to still take care of, and we didn't take care of model consistent fading yet. So that is something we need to impose in the future work. So this brings us to part C of this work, and I'd like to take any questions on part B.
If there are any quick questions, you can also, people online can also post a question on chat, and you can either address it now or later in the open session.
Right.
Yeah, you need to take a break.
Okay. So now we'll move on to part C. So we discussed already that while the computation of turbulent flows is expensive, but what is even more expensive are turbulent flows in the presence of wall. And the reason is the size of the energy containing structures near the wall becomes smaller and smaller as you approach the wall. As a result, the grid for LES is pretty similar to the grid you would have for DLS. So if you look at the two red boxes on the left, the cost is almost similar. So hence, we need methods which can reduce this complexity, and one of the approach is wall model LES. So we are going to use finite element projections to improve and understand what is the improve existing wall models, and also understand what is the effect of under resolution near the wall. But before we move on to discussing how to improve existing wall models, we'll discuss some of the.
So you're doing pretty well on time, so you can slow down if you want.
Okay. So we'll discuss some of the wall models that are commonly used. The first one is the equilibrium wall model, wall stress-based model. In this model, what you essentially do is that you sample the velocity at a grid point above, and then try to use equilibrium wall profiles to get the stress at the wall, and then finally apply the stress as a boundary condition. The other approach that can be used is the slip wall based wall model, where actually you pose a slip velocity rather than a no slip condition. So it might be, it is very counterintuitive to think that why is there a slip velocity, and because the wall essentially satisfies no slip. And the reason is because the wall is, the core scale doesn't satisfy the no slip, but the actual solution does, but we are just solving for the core scale. And one of the explanation can be given by using a differential filter, but we are going to use other kind of filters, which has finite element projections, to explain the slip. And this is precisely what we do. We again perform L2 projection of the solution to obtain the core scale. If you look at what L2 projection does, it is not something that is very uncommon to most of the people, because most people actually use the sharp spectral filter, which is essentially L2 projection on the Fourier basis functions. But with finite elements, it is now possible to actually do filtering in the near wall region and in the non-periodic directions as well. So there are choice of basis functions that can be used. Either you can use the CG basis functions or you can use the DG basis functions. And that is based on what application and how much computation resources we are going to actually use both of them. So first we will just use the CG projection onto CG basis functions. So if you look at this plot, this is essentially the projection of DNS on different meshes. And each of these meshes have certain properties. These meshes have properties which you would typically use in this these methods. For example, in LES, you would have all your length, all your delta X, delta Y, delta Z near the wall scale with wall units. For wall model LES, it would be essentially scaling with the boundary layer thickness. For hybrid lines LES, in the span wise and the streamwise direction, it scales with delta, but in the wall normal direction, it scales with 1. And the fourth one is essentially very coarse. The goal is to develop a unifying perspective with among all these methods. Essentially, if you look the solution of the coarse scale, you would actually see that these solutions actually look like the solutions you would essentially get in these methods, essentially meaning that you can now do a priori testing on these methods. And one of the observations on wall normal under resolution is the effect, the presence of slip velocity for the wall normal under resolved case. But those projections that we did on CG basis functions will be very expensive for the 5200 case, which is extremely big, and we want to simplify this problem. So what we did, rather than doing the full projection, we went to the near wall region, extracted a cube. The cube has equal sides, and then projected the solution inside the cube into a coarse P3 basis function, essentially filtering the solution. And immediately what you observe is the presence of slip. The DNS solution shown in the bottom figures satisfies the slip, satisfies the no slip boundary condition, but the P3 projected solution doesn't. This is also shown in the plots on the right, where you can actually see that there is a slip velocity. Also, you can also compute the pre-multiplied gradients, which is essentially the delta times del UH by del Y in the wall normal direction, essentially allowing you to compute the slip wall model coefficient, which we want to actually find using a priori analysis. But before we show plots how CW varies with delta plus, we want to draw insights and show how this work connects to part A and part B. So if you look at what slip velocity is, it is essentially the subscale, because the true solution will satisfy the no slip, and the coarse solution is essentially the slip velocity. So your subscale is essentially the slip velocity. And we are actually connecting it to the coarse scale using the slip wall model. Also, we also want our modeling to be done in non-dimensionalized setting. So some of the parameters that can be used is essentially delta plus or a Reynolds number based on slip velocity. Also, what we want to do is we want to use different size filters so that we can know what is the effect of grid on the CW, and this is what point 4 is about. And finally, we should only learn the part of the solution that is required, because in this problem, the only unclosed term is essentially the slip velocity at the wall. So the plot on the left shows CW as a function of delta plus, which is the size of the grid normalized with the wall units. One thing is pretty clear, that CW is not constant and has dependence on wall units. The second important point is that CW actually varies in the direction. If you consider CW in the streamwise direction, it's different from the CW in the spanwise and wall normal direction. Also, there is an effect on P. So whatever projection order you use, the CW actually depends on that. So, which is an issue because you don't want to create CW models for each and every numerical method. So there is a need for unifying the different projection or the effect of different projection orders through a common parameter. And this is what we will be doing here. So we actually found a scaling that pre-multiplies the resolution, which when goes into model 1 actually gives you the solution of the other projection order. Essentially meaning that you can just learn one model form and a parameter and then make it work for any numerical method. And this is really great because it effectively is similar to the Smagorinsky model coefficient, kind of similar, not exactly, where the effect of numerical method can be also changed by changing CS. However, it's really the case when the predictions from a priori testing actually match to your actual results. And to understand the effect of suboptimal subgrid modeling, because if you look at the a priori cases, these are all generated by filtering data, which means your subgrid modeling is perfect, but really it is the case. So to find what is the effect of the error in the subgrid modeling, what we do is we take the equilibrium wall stress model solutions and find what is the effective slip velocity that the model satisfies. Effectively meaning that if we can find an equivalence, we can actually improve the existing slip wall models. So what we observed that for lower delta plus, there was a discrepancy, but for higher delta plus, both the models essentially collapsed onto the same curve. Another issue is if you use delta plus as a feature, you need wall stress a priori to compute delta plus. However, if you use the slip Reynolds number as a feature, you would essentially find you know already the slip velocity, so it is a better feature to use. So we use the second feature. However, one problem still exists. All our a priori analysis has been done is assuming that the filter size is same in all directions. So we need to find an effective filter size. So what we observed that if you use the Smagorinsky model, you can actually replace your delta with an effective filter size of the cell volume, and then you can make the same model work for different aspect ratios as well. And below are some of the plots for a resolution that is unknown to the model in which it was fitted. And it shows that it actually is great because the existing slip wall model cannot actually be so predictive. And we could actually show in a priori performance that this model actually generalizes to different resolutions and Reynolds numbers. So in summary, we can say that the slip velocity is a natural consequence of wall normal under resolution. We actually provided an alternative explanation for slip, and we also showed that the VMS method can be used as a unified formulation for both subgrid modeling and wall modeling. We showed that the slip wall model coefficients are different in different directions. There is always effect of numerical scheme on these parameters, and we also established an equivalence between the existing traditional wall model solution and the slip wall model solution, and showed that we can actually use the second to improve the first. And finally, we found a single parameter to actually take care of all the effects of numerical methods. And we showed that our proposed model actually works on different resolutions and Reynolds number. So this brings us to end of part C, and I'd like to take any questions again if you have in part C.
Everyone is also out of breath because you're going so fast.
Okay. So this brings us to some of the contributions of this thesis. So first, we actually derived an MZ VMS model for the continuous Galerkin method and used it on different problems, starting from one-dimensional Burgers equation to incompressible turbulence. We actually improved the robustness and accuracy of the MZ VMS framework by actually dynamically finding what the memory length would be. We actually found that learning the projected subscales is equivalent to learning the projected Green's function. And we also developed a VSRNN architecture that is consistent with existing VMS formulations. Using this formulation, by using this formulation and training it on a sequence of low order and high order solution, we could actually make a framework that can learn the subscales pretty accurately And when these subscales were actually used for two of those problems, linear advection and LES or turbulent channel flow, we could actually find that we could improve the solution. We also developed a unifying perspective through finite element projections between different methods such as LES, hybrid lens LES, wall model LES. We also established a link between the slip velocity and in the wall model LES solution and the slip velocity that is naturally obtained through Weber's projections. We also made the existing state-of-the-art slip wall model work on different resolutions and Reynolds number. In addition to some of these research works, we also did some code development which were used to compute the results. The first one is CASLab CT, which uses which is a continuous Galerkin solver with PETC library. The second one is MPI-based high-order DG solver that uses the RK3, RK4 explicit time stepping and has wall model LES capability. Finally, I would like to end this presentation with some of the perspectives that apply to a wide scale of problems, not just individually to part A, part B, and part C. The basic idea is that we should always look for generalization, and that can be done through non-dimensionalization. You should always non-dimensionalize things. If you know the structure of the solution, you should always impose it in the model. You should not allow the model to actually learn it. One of the important properties is that if you have a numerical discretization, the closure modeling should be intimately linked, which means you should know what you are resolving and what you are not. And there can be cases where your formal methods might not work as accurate as your phenomenological models, and it is always okay to actually blend them. Even if you cannot learn these methods formally, you can always use data-driven methods that we do in part B. And that is a point that we have not considered in this work is model consistent training, which should be taken care of in the future work. And these are some of the publications that came from this work. And I would also like to thank the funding agencies. The part A of this work was funded by AFOSR, part B and part C was funded by NASA. And I would also like to thank Dr. Eric and Dr. David for all their help during my PhD. And I would like to thank everyone who made this experience really wonderful. And I would like to take any questions that you have. Thank you.
42 minutes, FYI, which is shocking, but right. Questions? Yeah, let me first take questions from those who are here, and then I'll open it up to those who are online.
Aniruddhe, very exciting work. So in the super resolution case, I think part B, you always looked at the predefined solution to get the higher resolution. Was there a reason to look for just the predefined solution? Can you go for edge refinement?
Oh, because we want to actually make a model for subscale. Because if you are doing the edge refinement, you are changing the mesh. But if you are doing a p-refinement, the P3 minus P1 solution is an estimate of subscale and can be used to close the solution.
And the difference that you're calculating is that sort of like
subscale, yeah.
I see, okay.
Other questions? All right, so let's go back to the first part. Two questions I can ask in the sort of general nature. Towards the end of the first part. Yeah, the slide before.
Yeah,
so slide before this. No. Just go to the end of the first part and then go one slide up.
This.
Okay, so first part is end of. Go to the end of MZVMS.
Okay.
Yeah. Sorry. Yeah. Yeah, this slide. Yeah.
Yeah.
So, first, let's talk about orthogonal subscales.
Right.
So, would you consider that to be the state of the art outside of your work as far as BMS goes?
I think this one was based on a linear orthogonal subscale approach, but there is a nonlinear version as well, which came in, I think, 2007, and we haven't actually compared it. But in general, it's very hard to beat the resolution, irrespective of whatever model it is, and that is kind of the common behavior that we observe.
Okay, so assuming that is representative of the state of the art, and maybe you have some improvements, maybe you don't. You made this comment that all BMS-based models only predict cross stresses. Can you is that a hypothesis, or can you rigorously prove it?
It's an hypothesis and based on observation, but again, people can call a BMS with a Smagorinsky operator as well. So it's hard to actually say what BMS is, as long as it's like formal.
So that comment is not quite right.
Right.
Maybe BMS with a certain class of approximations can only do the cross stresses, right? Especially if you're going the Green's functions approach.
Right. Essentially, I would say that if you are using a linear kind of an approach to get a form of the subscale and using it in a nonlinear problem, then you would have this problem in the
setting. So then that statement is not quite correct. All right. Other questions from anyone online? You can just unmute. There are only like a dozen people. Okay. So Vishal, why don't you go ahead and unmute yourself and ask the question? Unless you want me to read it out for some reason, I can do that.
No, it's fine. I was just eating, so sorry. Yeah, what are the advantages of VSRNN over, available methods like DeepONets or something?
I think that architecture is pretty similar, but again, this is like tied to what we are doing. So inspired from there. So yeah, I mean, I think there is kind of universality in everything. So
okay, all right, thanks.
Yeah, I think that's more to do with the way you non-dimensionalize and the way you bring together different parts. But it has similarities to branch and trunk net, but I wouldn't say they are.
Yeah.
Okay. All right.
It has, I mean, yes, I think all these methods have a lot of similarities in principle with a lot of multi-resolution networks. I have more questions about that, but we'll save that for the closed session.
Yeah.
So actually, I do have a question which I would have otherwise asked later, but because there was a question on subgrid scale. So you talk about super resolution, and you talked about it in the context of subgrid scale modeling, right? And you're looking at the difference between certain levels of P, polynomial order. Now, I mean, it's kind of picking up, it's nitpicking, but a lot of subgrid scale modeling has otherwise been done with what is called bubble functions, and you mentioned that. Right. So now when you look at the difference between P1 and P3, for instance, you are actually picking up some, what I may say, well, they're not only subgrid scale, you're picking up some global scales because P3 will presumably resolve better even on your the nodes that, So discuss comments.
So basically this is what we are actually showing discontinuous Galerkin work after this. So the work before that I was showing, this work, here we have actually learned the bubble functions. We have actually assumed that the coarse solution is an endpoint interpolate and then learn the solution. Pretty much what we are doing here, that this solution is essentially the difference and then we are projecting the solution. So for the CG approach, yes. For the DG approach, it is actually, so we were just trying to use this approach to improve the results, but actually what essentially is that would be the best thing to do for DG method is just learn the subscales at the boundaries, because that's what matters rather than what we are doing here. This
at the boundary of the domain.
Yeah, the fluxes, right.
Of the element boundaries.
Right. We are just trying to use it somehow to actually improve methods. This is, if you look at the way it is essentially doing, if you know that second order finite element volume methods, you actually reconstruct using the surrounding state your gradient. So this is kind of similar, but we're using a physics-informed approach and data-driven approach to do the interpolation. So yeah, it fits there.
But I would pick on that comment also because I don't think it's necessary that ideally you should only learn what's happening at the element boundaries.
Right.
That's
right.
true if everything else is correct.
Right. So it depends. It depends. It depends on whether it's a nonlinear problem or linear problem. So if it's a nonlinear problem, then it will have subscale contributions from inside as well.
Yeah.
For that linear direction, for example, there is only contribution from the wall because it becomes orthogonal and it just cancels out in the interior flux.
Okay. Any other questions? Last call. All right, if not, we're going to go into a closed session, but then we thank Aniruddhe for nice presentation. And, at this point, everyone except the committee can leave the room and leave Zoom. Again, thank you for your participation. It's not recording.
Fine.
Unfortunately, they.
No, but you're on. You're on.
So much easier.
That's all I'm
to
saying.
say. The amount that